Welcome back, troops. Okay, this is experimental gas laws, and this is about problem solving with the experimental gas laws. Just a reminder here of gas laws. First three, Charles, Boyle's, and pressure. Look at the caveats there. So the first law holds for a constant pressure, the second there for a constant temperature. And if the volume's constant, then the pressure law holds, those three there. And then we can combine all those three of them into a fourth general rule, which where they all vary. Okay, so keep those in mind, and we looked at them last time. So with those in mind, okay, here's the first thing to do: a little starter activity. So you can pause now. And moving on. Here we go. So let's have a look at the answers for this. Check your answers. They are quite tricky, these ones. So let's check them. Whoops. Let's put the answers in and check them. So they should all be correct there. Right. So why are we getting these answers? Let me go through explaining it. Let's get the magic camera up. Can we see the magic camera already? Right. First one. Doubling the absolute temperature of a gas will double its pressure. Doubling the absolute temperature will double its pressure. Is that true? Well, I think so, because we know that P over T is a constant. So if we times that by 2, we have to times that by 2, okay? So that should do it. Is there another way we can do it? I believe there might be. Let's have a look. P V over T is a constant. That's the combined one. If we keep the volume the same, if we double that, we have to double that. Yeah, so an application of that. Okay. Second one, the pressure and the volume are directly proportional to one another. No, they're not, because pressure and volume multiplied together give a constant. So pressure is directly proportional to 1 over the volume. So that's why that one's false. Okay. Let's have a look at the third one. Increasing the pressure by a factor of 10 will always make the volume 10 times smaller. Not necessarily so, because we know that PV over T has to be a constant. So what are they saying? If we increase the pressure by 10, they are saying, do we have to make the volume smaller by 10? No, because we could make the temperature bigger by 10 if we so wished. Okay, so in other words, that's false. Next one. Heating a gas at constant pressure will lead to an increasing volume. So the pressure is constant, okay, and we're heating the gas, so this law applies. Volume over temperature is constant. So therefore, if we increase the volume, rather, if we increase the temperature, we increase the volume. Does that make sense? Makes sense to me, because we have a fixed pressure. Okay, and the fifth one. The gas laws change depending on the type of gas in question. No, that's false. That's false, because we're thinking about gases in an ideal way here, and these are very sort of simple models of gases, and we can apply it to most gases. So that's the true or false. Okay, let's move on then. So think about those. They are tricky. Okay. Now then, you should be reading around this subject quite a lot. This is the text that is available to you. You should be reading this. This is the school text and where some of the questions come from. And here are some questions that I am going to set you. 1, 2, and 3 for definite. Have a go at them now. Pause them. Come back to this video later if you haven't done them already. But here's a big clue. Question 1, 2, and 3. If you look on the screen there, 1 is solved by using Boyle's law, and then pressure law and Charles' law. You can read that. So pause that. Do it. Come back later. Okay, so we're back now. So here's the solution to question number 1. There you go, that's fine. Let's get the camera up, the magic camera. Good, 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 good. Now, question 1. You've got to draw a picture. You have to draw a picture of the physical situation, what's going on, to get your head around it. And the question was slightly misleading in a way. It didn't give you absolutely everything, but here we go. Let's have a look. We've got a pump connected to a container. Now, basically a pump, I'm going to draw here. Here's a pump. It's basically a syringe, a pump, isn't it? And here you go. There's the air in there. We can push that. And this is connected to some sort of container that's obviously closed like that. Okay. Now, it tells us here that the hand pump has a volume of this meters cubed, and this has a volume of, I believe it's 8 times 10 to the minus 4 meters cubed. Okay. So let's have a think. What's actually happening physically? It tells us that initially the air pressure is 101 kilopascals. Now that's atmospheric pressure. So the pressure in the pump, the pressure in this volume here, because they are connected, the pump's connected, they're both at the same pressure, and it's room standard pressure. Okay, that's the before situation. Now when we pump, this is what's happening. Okay, now we have squashed the air by pushing that plunger, and so all that volume that we initially had has been squashed into here. So this volume is still 8 times 10 to the minus 4 meters cubed. This has got no volume now. So this is an application of, it must be Boyle's law, because we're looking at pressure and volume. And we know that, let's put it here, we know that pressure times volume is a constant. Okay. Our volume here, our pressure volume combination here is, add these two up. So our pressure, let's call that P1, is 101 kilopascals. Our volume V1, let's call it, is that, add that. And if you add those two together, look, that makes 10 times 10 to the minus 4. I know that mathematics don't like you doing that, but tough. Okay. So I'm going to write down a statement, because we now have a volume, we have a new pressure that we don't know. We know the volume of that, and we'll call that V2. We know that volume there is 8 times 10 to the minus 4. So we've got one unknown quantity. Let's solve this. Let's solve it. Okay. So I'm just going to say that P1 V1 equals P2 V2. Does that make sense? Let's rearrange it, because I'm looking for P2. So let's say that P1 V1 divided by V2 equals P2. Okay. And you know what, kids? I haven't left enough room there to do any proper calculations. Let's shift you up a bit. Let's shift you up a bit. There we go. So let's rewrite it here. Look. P1 V1 over V2 equals P2. We know what P1 is, because that was up there. P1 is that 101 kilopascals. We know what V1 is. V1 is that total volume that we started with, all of that, look. That's times by 10 to the power of 4, to minus 4. So let's get rid of that. Divide it by V2. V2 we know is that. That's V2. 8 times 10 to the minus 4. Let's get the calculator out. That's what my kids used to call a calculator. It comes from the tweenies, if you remember them. Calculator, right, let's have a look. So we have 101, whoops, 101 to the power of 3 times by 10 times 10 to the power of 4 equals, divide it by 8 to the minus 4 equals, gosh, I've done a calculation error there. Let's do this again. 101. Do you know what I'm doing, kids? Look. I'm typing all these exponents in. Don't need that. Look, that cancels with that. Let's make life easy. 101 to the power of 3 times into the 3, times by 10 equals, divide that by 8 equals, the number comes out 126250. 3 significant figures, 130000, or no, 1260. So 126 kilopascals. Okay, and that makes sense. Okay, makes sense because we started off with all of this big volume at that pressure, and then we squashed all the air in. So obviously there's more particles trying to get out of this now, bumping around. And so that pressure's gone up now to 126 kilopascals. And it's in the same order of magnitude. Always look out for that. They're both the similar sort of order of magnitude and size. So that entirely makes sense. Okay. Now the trick here to these sorts of questions is you have to draw a picture, get an idea of physically what's going on. Here's the pump connected to the thing. That could be a football, could be anything. And a pump basically is working like a syringe, isn't it? Okay, you all know what a syringe looks like, the things that you stick medicine in and whatnot. And then draw the after picture, what's happening, and you can see that the volume taken up by the gas is obviously being decreased, and so on and so forth. And then we're applying our formula. Okay, so that's example number 1. Make sure you've got your head around that. You've seen me do it now. If you haven't done it already and you haven't corrected it, don't just copy this down. Go away, have a go, and see if you can get the answer that I got. Okay, so good. Let's pause that for a minute then. Hello, right, can we do question 3? No, we're not doing question 3, are we? We're doing question 2. Been a nana here. Right, here's question 2. Can we do question 2 in 3 minutes, which is the time left on this recording? Yes, we can. Okay, so we've got a sealed container. Let's draw a picture. Sealed container. Okay, it's got a pressure of 101 kilopascals. It's got a temperature of 100 degrees C. Don't fall for that one, children. 373 Kelvin. Okay, turn it to Kelvin. We cooled it down. It's a fixed volume. We can't change the volume. And pressure, the second pressure is what we're looking for. And we know the new temperature, temperature 2, is, what was the temperature? It says 20 degrees C. Don't fall for it. That's going to be 293 Kelvin. Okay, not percent. Okay, so constant volume, pressure and temperature. What is the relationship? P1 over T1, pressure over time over temperature is a constant, so therefore we get that. Okay, we are looking for, what are we actually looking for? We're looking for P2, so rearrange P1 over T1 times by temperature 2 equals P2. Let's sub our numbers in. P1 is 101 times 10 to the power of 3 times by temperature 2, which was 293, divided by the starting temperature, which was 373. Okay, let's get out the calculator. I've got 1 minute and 20 seconds left of video time. 101 to the power of 3 times by 293, the pressure's on, children, equals, divided by 373 equals 79337, blah, 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 blah. So that's equal to 79 kilopascals. Bazinga. I do believe that's the correct answer. Let's have a check on my correct answer list. 79 kilopascals. Phew, with 45 seconds to spare. So the next video is going to be really short, looking at question 3. Okay. Do review your notes. Keep on reading. Reading is good. That's how you learn stuff. Okay. Enjoy. Till next time.